Hello and welcome to 7th lecture of course on data-enabled tribological engineering from experiments to predictive model. Topic of this lecture is lubrication regimes and film thickness calculation. We will not be doing calculation of film thickness in this. Maybe later 8th, 9th, 10th, 11th lecture will be doing some sort of calculation. But here we are trying to give elementary analysis to understand the film thickness relevance related to lubrication regime. Now, when we start with this course, naturally there is a need to revise something what we have learned in previous lecture. There's a lecture 6 where we say the real area of contact when the two surfaces come into contact is far lesser than apparent area of contact. So this is a very important concept which is really required. And this figure was shown showing that the overall area may be maybe this to this line to this line, or maybe this point to this point, and then apparent area can be multiplied. If I say this is a L and this is a W, then apparent area will be L into W. But if you look at this, contact happens only in a few spots. That means area of contact of this one asperity, second asperity, third, fourth, fifth, 6, 7, 8, 9, maybe 10, 11, 12, whatever. And whatever area we need to sum up, that area will make a real area of contact. Naturally, that area of contact will be very low compared to the apparent area of contact. At least I have seen in literature it reaches up to maximum 15%. If surface roughness is almost negligible, extra smooth surface, then area of contact will increase, but more or less we have seen the area of contact is not coming maximum to 15%. This figure also was shown related to gear pair, where we say there is a one driving gear, another one the driven gear. When we enlarge on a nano scale, we are able to see the roughness of the gear profile also. So this is important to understand. And then even the lubricant passes inside and exit from this side, still will not be a complete separation between two surfaces. This will be thin film lubrication, and that was shown in this kind of figure, the oil in and oil out from this point of view. And we mentioned very clearly accounting surface roughness is very important to understand the tribology in proper way. Of course, to compare it, we also took example of the thick film lubrication. We say the two surfaces are completely separated, and this is a typical example of a hydrodynamic lubrication. So that's why we say lubricant or lubrication and lubrication regime need to be understood together. So this is a hydrodynamic lubrication mechanism. Even though I'm using the word hydrodynamic, but if lubricant is air or gas, then it will turn out to be aerodynamic. Of course, the principle will be remaining more or less same. Equations will change to some extent, and complexity of aerodynamic mechanism will be slightly more involved, maybe say slightly more difficult compared to the hydrodynamic. Now we also have shown this kind of figure. We say that recent trend is that we go for the low viscosity instead of going for high viscosity. Reason being, initially the coefficient of friction is slightly higher for the low viscosity, but at the later part coefficient of friction is much lower. And if we know that major portion of the lubrication of the mechanism will happen in this side, then why not we go with a low viscosity in this case. And maybe we can add some sort of nano additives. Nano additives maybe can be graphene, can be MOS2, or whatever is really relevant to that. So this is what we can say. We can go with nano additives with a low viscosity oil. That will be really much more beneficial. So that's what we say. Recent trend is that going from shifting from thick lubrication to thin lubrication, and where the surface roughness has to be accounted appropriately to get the right results. And to understand that, we will introduce a new parameter. That's what we call a surface with a specific film thickness accounting the surface roughness, and it has been given as the H minimum divided by composite surface roughness, that means RMS of surface A and RMS of surface B. And this same parameter was defined in the first lecture where it was clearly mentioned, and in the previous lecture or sixth lecture also we defined this parameter, specific film thickness, and that specific film thickness really divide the lubrication regime. How? That's where we are showing this kind of figure. Is again a Strybeck curve picked up from a literature. You can see here that when Strybeck curve is almost negligible, and then even a specific film thickness is also very low, and where we are saying the average film thickness in this domain will be roughly nanometer 5 to 10 or 100 nanometer maximum in the situation. So it is in a nanometer level, 5 nanometer to 10 nanometer, 100 nanometer, something like that, depending on the surface roughness. If the surface roughness is on a higher side, even a higher thickness possible, but generally in recent days we are looking forward a better and better surface finish. And in this case, specific film thickness is lesser than 1. We say specific film thickness is ranging between 1 to 3, then it will be known or maybe treated as a mixed lubrication, which happens in most of the cases. Of course, we always aim for the elastohydrodynamic lubrication. However, the drawback of elastohydrodynamic lubrication is that we have very narrow range. That means whatever we do, it has to be designed appropriately or maybe with 100% correction. If little bit shift, it will move to the mixed lubrication. So like most of the gear pair which I have seen, they work in a mixed lubrication. Again, this parameter and then up to 3, it's also subjective. Some books says that mixed lubrication will happen between the 1 to 2, or specific film thickness more than 1 but lesser than 2. Again, hydrodynamic lubrication, which we are writing that the specific film thickness need to be more than 10, but is again a subjective. In some books they write this as a 3, some book they write as a 5, some books they write a 10. So it is a subjective. However, if there is a clear separation between two surfaces and sufficient hydrodynamic film is there, then we will call hydrodynamic lubrication mechanism, otherwise not. Even in that situation, at the beginning and towards the end of operation, again we will be moving from hydrodynamic lubrication to the boundary lubrication, which is a drawback to some extent of hydrodynamic lubrication. So that's why I'm using the word, it is a subjective. Whatever the data which is available in literature, they are subjective. That's why we need to refine, we need to update, and we need to come up with better algorithms. Along with the Strybeck curve, sometimes this kind of relative ranking of the wear rate also been quoted. We say in even though in a hydrodynamic lubrication, friction is on higher side, but wear will be much lower side. So where we want to give more weightage, if we are ready to sacrifice to some extent the energy, but we are more we say the pro to do not go at all for the wear rate, then we will prefer to go for hydrodynamic lubrication. Otherwise, if we want minimum friction and minimum wear, then we will be choosing elastohydrodynamic lubrication. Of course, with the time, all the lubrication mechanism will move to the boundary lubrication, because with a wear or with the time wear will happen, and with a wear surface roughness will be deteriorated. With that, specific film thickness will come down, and with that it will move from elastohydrodynamic to the boundary, or maybe hydrodynamic to EHL to the boundary. So there is a continuous process and we need to account it. So that's why I say even ideal lubrication mechanism in my view is elastohydrodynamic lubrication mechanism. That means almost all the tribopair should be designed keeping in mind that we want to achieve elastohydrodynamic lubrication. However, this range is very narrow range. It's not a broad range. That means operating parameters need to be well within limit. Even the load, speed, viscosity, temperature, pressure, surface area, even the roughness, everything need to be well within control. Once we are not able to meet that, then naturally there will be kind of the failure of thin film lubrication, and then it will move to the boundary lubrication mechanism. So we want to achieve thin film lubrication. Again, it is in very narrow range, and we need to have continuous monitoring, and we need to choose right parameters. Then only we will be able to achieve the right results. Just to add what I have said in previous slide, we say in this case you can see the wear rate. Now wear rate has been compared for the two cases. One is a BL is stand for boundary lubrication. Other one is SDL, is a hydrodynamic lubrication mechanism. You are able to see very clearly the, in this case, whatever maybe say this is a suppose X wear rate, this will be around 10x to 100x also BL. That means hydrodynamic lubrication is far better compared to BL. However, this is a for the comparison only between BL and SDL, but more or less this also same thing will happen with ESDL also. Elastohydrodynamic lubrication mechanism, if I assume, or we can say directly EHL case. More or less similar kind of curve will come in this case also. But you see this figure which says very clearly with a time surface degradation will occur. Initially there is a wear in, that means initially surface roughness will be on the higher side, that's what we call a running in. And when you buy a new car, you are being asked only to drive at a 40 kilometer, 50 kilometer, 60 kilometer per hour maximum. Don't go beyond that. That is what we call a running in time. When the two surfaces are coming with each other, are coming in contact with each other, they try to rub or maybe say lap each other, so the surface roughness is improved. And almost all the type of surfaces running in behavior will occur. They will improve surface roughness, and then maybe say initially suppose there is a 0.1 micron value, it may turn out to 0.05, 0.03, 0.01 with a time in particularly in running in time. That means this portion will be there, but still after that, that again the wear rate will be on a higher side. Maybe say wear rate not absolutely on higher side, but relatively it is a slight higher compared to this one also. So this is a cumulative wear volume. Initially it will be we don't count, that is what we call a zero wear, and running in time it is really required. After that the measurable wear comes, and then here we say that this slope, if we are able to control, keep it minimum value, and then maybe say instead of this, if I come to this line, it will be always a preferable, and that why we require a lubrication. When you come on the lubrication, you can see the wear coefficients which has been tabulated. Says very clearly the solid lubrication gives a worst wear coefficient, then boundary lubrication, then ESD, and this is same elastohydrodynamic lubrication mechanism, and finally comes to hydrodynamic lubrication. This indicates very clearly out of 10 is to 13 particles of location, one location will wear out. So there is a probability, almost insignificant probability of the failure, but still there is a probability. And one of the major drawback has been quoted in this case also. In a hydrodynamic lubrication, initial wear, the beginning itself will be higher, and friction will be much more higher compared to this, that is indicated 0.25. In real case it may not be, but this is a kind of value has been quoted, or maybe less available literature, and the kinetic coefficient of friction is decreased significantly. And because of this huge variation between this coefficient of the friction, static and kinetic, sometimes we get some sort of a friction instability also. If you want to read something on friction instability, please refer my book. Complete it has been explained how the friction instability starts. So this is one possibility in this case. Coming to the rolling element bearing, you can see here the coefficient of friction is much lower, kinetic as well as static, but it is even in this case is far lower compared to the static, while in coming to the kinetic coefficient of friction, it is almost matching. So that's why the many times the sliding bearing have been replaced with the rolling element bearing. Possibility is there, of course. So we know that special rolling element bearing manufacturing is costly, but if it is really required in bulk, maybe say a million pieces, then rolling element bearing will turn out to be much cheaper compared to hydrodynamic, particularly when we are talking about static friction and maybe energy loss, accounting energy loss, then this will turn out to be much cheaper. So we need to think tribology in a slightly different manner, which kind of lubrication region, which kind of lubricant, and how we are retaining, what will be the effect of temperature, what will be effect of the pressure, what will be effect of the environment, what will be effect of the time. Can we control this slope also? If it is, then it is much more meaningful. Otherwise, we will not be able to predict the life or predict the friction model, or maybe say estimate the wear model or possibility of the wear rate easily. So we really require complete analysis of that. And with this data, I can say that service life in hydrodynamic lubrication naturally will be much higher. Even I can say higher and higher, much greater than service life in bonded lubrication. So that's why the hydrodynamic lubrication is required. But again, as I mentioned, that there is a friction limit. So we prefer to go with the elastro hydrodynamic lubrication mechanism compared to HDL. However, there is also drawback of the HDL in the elastomeric lubrication. The range which we are deciding is much narrow compared to the hydrodynamic lubrication. So we need to account those things. So in this figure, we have shown that how the lubrication mechanisms shift. So we have given one number as a unlubricated, two number as a boundary lubrication, third number as a fluid film lubrication, FFL in this case. And it has been very clearly mentioned the material pairs are same, lubricant whatever we are using is same in both the boundary and FFL case. Viscosity, geometry, finish, lubricant quantity, all these are the same. So the comparative study can be made. And it also in this case can be seen that figure that this 2 is moving to 1, 2 is moving to 1, 2 is moving to 1. And that's what I'm meaning, that if the boundary lubrication fails to provide sufficient protection, we will be getting some sort of adhesive wear, and that will causes a major problem, and finally kind of the welding of the surfaces. And that is if there is a more and more torque is applied, the surface roughness will maybe because a cold junction will form, break, and then it will change the surface roughness. So what we can say here, the transition from a fluid film lubrication regime to bonded lubrication in response to increase in the load, or in this case, or contact pressure, though those are the same, or oil temperature, that has been also shown here. That means if I increase the temperature, fluid film lubrication will move to the boundary lubrication, and with more temperature increase it will move to unlubricated case. That means temperature plays a major role. With increase in a temperature, even though we are providing lubricant, it is not really giving much more meaningful result. That means we need to choose a lubricant appropriately. That's why I say that we need to think about lubricant and lubricant regime together and get a solution. In this situation, if we are choosing a low viscosity oil, we can choose a nano additives, or we choose some additives which can really give a desirable property. So naturally we need to know what are the desirable properties. Am I really aiming to go for the antioxidant additives? Am I thinking about anti-corrosion, or am I really thinking about extreme pressure additives? So those things need to be added in the lubricant, and we need to design a lubricant appropriately. And that's why we say that transitions are associated in alteration in friction coefficient and wear rate. Here in this case we have shown in all the three cases the wear rate. So with the time, the full film lubrication will move up. Now this can be 10 years, 15 years, 20 years, whatever we have designed. With the load, it will be much faster. With the temperature, it will be much faster. With the time, it shows much slower. That means we can control this parameter after understanding each the effect of the each parameter on the wear rate and friction and overall performance. Here some estimation has been given that unlubricated wear rate will be almost 10 is to 5 times of a boundary lubrication wear rate, and 10 is to 10 times of compared to the full film lubrication. Again, these are the subjective decisions. We can't say exactly, but this is a just indicative that we need to be very careful when we are designing the product or designing the surfaces which are going to move against each other. There is a relative motion. So this is only the subjective. Some books they refer, I'm quoting back in this manner. So it is not that you need to completely believe it. It's kind of some guidance that we prefer to go ahead with the EHL. As I mentioned, the wear rate in EHL and full film lubrication will vary to some extent, but not significantly. Only the drawback of the EHL is that it is a really narrow region, and if temperature goes beyond, pressure goes beyond limit, misalignment comes, then it will move to the mixed lubrication, boundary lubrication. If you want to play 100% success, someone will say, even you do not worry about a friction, but you want 100% safe, there should not be any wear rate at all, then we will go for hydrodynamic lubrication. But otherwise, with this not a requirement, if we have known all the parameters appropriately, I'll prefer to go with elastohydrodynamic lubrication. Whenever there is uncertainty related to misalignment, uncertainty to friction, or related to temperature, uncertainty related to some load parameter, then I will go with a hydrodynamic lubrication. Otherwise, there is no need as such. So this is what has been shown in this case, that you need to consider this figure, particularly this zone and this domain, how the transition is occurring. If it is possible, you try. Now, what is the major issue is that with the temperature, viscosity decreases drastically, and we know that to reduce this temperature dependency, we add the additives, what we call a viscosity index improver, which we have studied in previous lecture. But if we don't have those additives and then viscosity is decreasing drastically, then we are able to see the Strybeck now curve, that if viscosity decreases, this moves in this direction. That means even EH and hydrodynamic lubrication will move to EHL, to move to the mixed lubrication, move to the bonded lubrication. So this is a very sensitive parameter and we need to account appropriately. So now, if I want to summarize what we have studied to in the previous few slides, we say lubrication design, what is really required. We say that we need to consider concept appropriately. Now, if I assume the definition of the friction which is given in a book, say lubrication is required to reduce the friction only. Many people have a thinking that lubrication means to reduce the friction. They don't worry about the wear. So here I want to just quote few examples. See, when you drive car or motorbike on a dust, you will get a lesser friction. You will get a slippery road. Similarly, sand or similarly gravels. The slippery road, that gives a lesser friction but more wear rate. So this cannot be treated as a solid lubricant, or it is not right definition. What is our aim? Our objective should be we develop a lubricant with a low predictable friction. May not be zero, but we should be able to estimate friction appropriately, and it should not cause any damage to the tribose surface. So that's an object of lubrication or lubricant developing or designing lubricant. We say develop a lubricant with a low predictable friction, no damaging to tribose surface, and strongly what is desired. Say it should attach to the bearing surface. That means there should be strong addition to the bearing surface to minimize quick depletion. We know that if the operation, it is not under operation, it will deplete, it will move away from the surface. But when it is under operation, then quick depletion should not happen. Lubricant layer remains there for some time. So that is where we say that addition, it can be chemical, it can be physical, that should be there. Aim is to, or maybe desirable goal, say reduction in friction and wear. It's not only friction and wear. And then we should have some sort of a properties of the lubricant, what we call a solubility. Whatever additives we are mixing, we can get additives, but whatever we are mixing additives in oil, if they are not soluble, then it will not serve the purpose. So solubility of additives is required. Appropriate viscosity with a temperature, that means it should have a right relation between viscosity and temperature. It should not thin down so fast. It should have a heat capacity also, so the temperature rise should not go beyond certain limit. That means it should have some sort of a capacity to handle the heat. And another point, it should not corrode the surfaces. Many lubricant, they get oxidized, they become kind of the pH value comes down. Even initially is a 6.8, with the time it becomes a 6.5 and even 5.9 or 5.5. So that will create a corrosion environment for the surface. So instead of protecting the surface, they will damage the surface. So in that situation, we need to design lubricant appropriately. So that's what we say here. Choose right lubricant, but that is a major challenge. Reason being, we have a lot of data available Few data will say good, few data will say all right, maybe give some different kind of rating. So we need to really drive, we need to extract the right features, and then go with a data driven algorithm, so that which can really provide some sort of assistance for the optimum selection of the lubricant. That's it is very important for us to understand. First thing comes, why not we connect a travelologist with the computer engineers? They work together, they work in a collaboration. We should get a right results. However, it has been observed also that doesn't work completely. The one person has to have a more knowledge, maybe predicting the data, using the utilizing the data in appropriate manner. That's why this course has been framed, data enabled travelological engineering from experiment to predictive model. So we need to know mechanism as well as algorithms, so that we can choose right things. When you connecting only travelers with computer engineers, we are not getting 100% synergy. Just to avoid that kind of problem, the we get into the computer science and algorithms, understand and implement right algorithms. That's what we are planning to address all those issues in this course. And we say the ML, that's a machine learning application in lubrication, can significantly reduce trial error cost. Many times we say, okay, we'll mix 0.05%, 0.1%, 0.15%, 0.2%, we'll try. But without knowing detailed knowledge, if we are able to extract a good knowledge from literature, and then we are able to predict, okay, if I mix zero point 0.5, what will happen? If I add 0.05, what will happen? Based on that, we do lesser number of experiment, better results, that will boost economics, and that's why we say it will boost economic growth in the situation. So that's why we are trying to introduce machine learning algorithm in a lubrication, in a tribology, so that we get a better results. One more point comes that whenever we are talking about the lubrication regime and minimum film thickness calculation, we need to think also real-time monitoring of lubrication system. So I'm saying very clearly, there are enormous data in a tribological literature. There are machine learning algorithms also. On top of that, we need to come up with some sort of model which need to be validated. For that purpose, we really also required experimental data or experimentation as a for verification for final. It's not for complete thing. So real-time monitoring of lubrication system is very important to understand whatever we are predicting, or whatever we are investigating, is are we really reaching to the right solution or not. So we'll be covering some case studies towards the end to see whether whatever we have learned, is it really meaningful, is it really getting some right results or not. And this is what we see that it critical value condition of sliding contact and can be reduced, and we can increase machine functionality. So overall economic gains will be achieved when we understand this course properly, we implement course properly, and then we do also validate whatever we are predicting, are they really more meaningful or not. One of the major thing which I have learned, most of the literature they give only some knowledge, but also we have learned that there is some sort of surface degradation will be in the process completely and continuously, and then it will generate a debris. And now this debris can play dual role. That's what we say, that will be called interfacial wear mechanism, because there are a few free wear particles. Now it can do two things. Yeah, it can really roughen. If the surface initially is very good, smooth surface, it can roughen the surface. That means surface roughness can be damaged. While if there are rough surface and particle come, then there's a possibility it will give it a smoother surface, right? That means initial surface roughness is on higher side, but smoothing will happen. Whatever the case, either first or second case, specific film thickness is going to change with the time. So if I design at the beginning, oh, I'm going to keep this lambda greater than 1, quite possible after 50 hours it becomes a lesser. So that's why we need to predict, and that's why I say tribology is a time dependent. It is not that I design it initially, it will remain always like that. Maybe next hour this quite a specific film thickness will vary. Maybe after 10 hours again it will vary. 100 hours it again will vary. Am I able to predict that? That's where this question comes, and that's why this kind of course is required. So what we say, based on this, there will be a shift in lubrication regime. So we need to study all lubrication mechanism. It's not that, oh, I studied only hydrodynamic lubrication, I'm happy, or I understood only elapsed lubrication, I'm happy. No, we need to understand all lubrication mechanism, because there will be transition and we need to predict it. It is not that we understand only one lubrication mechanism and our tribopair is going to work in that. Quite possible tribopair will work in all the streams, or maybe in some local some contact it is under boundary lubrication, some contact it is under hydrodynamic lubrication, some contact maybe is under the last hydrodynamic lubrication. So we need to understand that, and that's why again we say the real-time lubrication monitoring is really required to examine the lubrication regime and find what will be the critical film thickness in this case. So that's very important for us. In lecture 6 also we thought about the designing lubricant. We say that we can now, with the present understanding, we can take oil as a carrier fluid having some viscosity, low viscosity. We use some sort of appropriate additives, and mineral oil being cheaper, and additives can be the synthesized. Maybe we can do some trial, or maybe we can extract the information from literature and come up with something, and then we look at whether the manufacturing companies or some lubricant companies are manufacturing that or not. If it is, then we can choose also, select also. So lubricant can be done. The question comes, how will I maintain, how will I retain lubrication layer on maybe say this kind of surface? How do I maintain, how do I retain this lubrication layer on this? And that's where the way new kind of lubricant which has been studied and extensively in past is a grease lubrication. We say it is not a solid, it's not a liquid. That's why we are using the word, it is semi-solid lubricant. And in my view, semi-solid lubricant having controllable properties will be very useful for us. Now, what are the advantages? We say it can maintain continuous contact with the moving surfaces. So that's whatever we are trying to address here. Quite possible the grease can be maintained there. It will not be wiped off so easily. Even with the finger we try to remove, still we find a thin layer is still on the contacting surface. So, and another thing is that it doesn't got leaked easily, so that it has some sort of sealing properties, and even the centrifugal force or maybe gravity force, it doesn't drip out easily, right? So this is what the major advantage, it doesn't get expelled out. Even in case of the rolling element bearing, it gets expelled out slowly. So we can charge it again once in a 14 days, once in a 7 days, once in 6 months, depending on the how much expellation of the lubricant is happening. So that's possible. So based on this property, I can say that grease provides a two lubrication regime together. Thickness, that's a part of the grease, will play a role at a low speed. The lower RPM, thickener will play a major role. At a high RPM or maybe more moderate RPM, moderate the speed, base oil will play more role, right? So it contains the two together, kind of solid and kind of liquid. That's why it is named as a semi-solid. It has a both. It has a thickness, which kind of the solid lubricant we can design accordingly, and it contain also lubricant. Major question comes, how solid lubricant contain the liquid lubricant? So naturally the structure plays a major role there, and that's what is shown here. This is a yellow color grease has been shown to you, and this kind of the black grease, not exactly, but molybdenum disulfide, if I go ahead it will give the black. In what we say in layman language, grease is a black or yellow sticky substance. Of course, now we can change color. Even I can get a white grease, I can get a blue grease also. There's a possible, right? However, in the layman language or maybe classical way, we say grease is something yellow or black, right? So the black and yellow substance which is used for the lubrication purpose. Now, what are the ingredients? Ingredient is a base oil. You can see base oil is 75% to 95%. That means majority of this lubricant is a base oil. We use some sort of thickness, that is what we say play a solid part. Base oil plays a liquid part, and we use also additives. it can have a several additives. It can have a graphene as additive. It can have molybdenum disulfide as additive. So whatever the properties we want the to improve the extreme pressure properties, anti-corrosion properties, or maybe say temperature should not affect much, that also properties. That manner we can add whatever we like to add in this case. Coming to the base oil, the way in previous lecture we understood, there are mineral oil, there are synthetic oil. We can make a grease out of mineral oil, we can make a grease out of the synthetic oil, and these are available products in the market. Now coming to the two different kind of oil, we say low viscosity oil and high viscosity oil. Depending what kind of the operating condition, we prefer the lower load, high speed, maybe really lesser temperature, low viscosity oil as a base oil. And coming to the high viscosity, high load, slow speed, moderate temperature, again if I'm using some sort of additives, this rating also will change. So it is not only restricted to these three parameters, the number of other things also will play a role. Coming to thickness, can be soap based thickener, non soap based thickeners. So we also have a huge variety of the thickeners also. So we have enormous material for the grease also. We have many type of greases. Additives, we, as I mentioned, we can have a choice. We can go ahead with some sort of oxidation reduction or antioxidant additives. We can go for the EP additives. E is stand for extreme, P stand for pressure, so extreme pressure additives. However, I don't prefer to use EP additives because they are kind of chemicals which will act with the surface, will make some sort of a sacrificial layer, will eat away slowly the materials. So unless it is very essential, we don't go with the EP additives because it will really deteriorate the surface. So instead of EP additives, I'll go with the anti-wear additives. We'll discuss this also maybe in future lectures. We can think about the corrosion inhibitors also. Like one of the calcium based grease is extensively used whenever there is some sort of water repellent requirement, or wherever there is a water related corrosion or rusting. That kind of grease also can be utilized, or maybe we can add the additives in this situation. So this is a microstructure of the grease has been shown. You can see this is a 2 micron scale, and you are able to see this kind of strand. These are the fibers, or what we say, the thickness fibers, right? It can be mixed also. Maybe I can use two separate materials, then it will be called a complex. Like I use a lithium grease, or can I use a lithium complex grease? That means I'm going to add something else along with that. That will enhance slightly temperature range. Maybe we can operate on a higher temperature range also. But you can see here, this they make a kind of web, and the lubricant is retained in that. So when the surface comes into contact and requires a lubricant and high pressure, or maybe a moderate load, then liquid will come out and it will go back also in that. So this is what we say, this complete thing is a sticky. It has something like a 75 to 95% oil, and this fiber, the kind of structure at the nano level, it looks like something like this. It is a kind of web. It is and intertwined in a manner the liquid cannot escape so easily, or we can use a word, liquid cannot bleed easily. That's where the overall structure is made. And one interesting point is that these thickness, then often are the soap base, which are cheaper, cost effective. And then if you want a low cost, we can go with a soap base. If you want high cost and maybe better property, far better property, we can go for the non soap base. However, lithium based grease, here not only lithium soap, lithium based grease has been extensively utilized. Major advantage is the service life. Even I have seen that even after 5 years of operation, this grease does not we say that deteriorates significantly. We can still continue it. So whenever the long service life is required, lithium grease really gives a far more advantage compared to other greases. So that's why the literature says almost 85% greases which are available are part, or maybe belong to the lithium grease domain. It can be simple lithium soap, it can be lithium complex, and that has been used extensively. So here I'm showing a three type of the greases: a lithium plus mineral oil, lithium plus ester, lithium plus silicon. The silicon is one of the best synthetic oil which can sustain very high temperature. That's why it is shown that in the grease which has been made with the lithium as a thickness, that can sustain 200 plus temperature also. However, the cost is on the higher side. Coming to the mineral oil, the max temperature we are able to can meet only the 150 degree, and cost is also on the medium side. Of course, you can go for the cheapest. The grease is a calcium based grease, which is used in most of the common places where we don't really require a good performance as such. I can use in cycle, I can use in doors, I can use in those places. But wherever really we require a good grease, where we are more worried about the performance, I'll prefer to go with a lithium based grease in the situation. Now, how do we quantify grease? Which grease is thin, which grease is thick, something like that, because we have been talking about the thin film lubrication, thick film lubrication. How do I quantify this? So, for that purpose, a National Lubricating Grease Institution has given some method, and that whatever we quantify, we use a word NLGI grade. Basically what they check the consistency, or in a more different word, material group, you say it check the hardness of the grease. Harder the grease, naturally NLGI grade will be on a hard side. And what is the most common grease which people use? If you don't have been defining anything, I'll go with NLGI grade 2. That's a what, that's a very important thing. However, if you want to go for thinner side, particularly for high operating speed, that's more important, then pumpability will be major issue. So that's why we'll go with NLJ lesser than 2, NLJ 1, NLJ 0, and that can be pumped also. Of course, not that kind of pumping power which really required for the liquid lubricant. We can choose NLJ lesser than 1, and basically for circulation system. And then one more what we say, people think about the liquid lubricant will give a lesser friction, and then the study says that it is not necessary. You can see here base oil A gives a high coefficient of friction at the beginning, or friction torque in the beginning, while coming to the lithium soap E gives a minimum friction, and you look at the transition is almost negligible. E start from here and then shifts here. The transition is not significant in this case. However, for the liquid, particularly base oil, you can see there is a significant change. Of course, there are other greases also: aluminum, calcium, sodium. Of course, in these days, the sodium grease we don't use at all, because it is not easy to make, as well as it reacts also. So calcium is one of the cost effective. If nothing is known, or maybe cost is a major consideration, performance not a major consideration, I'll go with a calcium based grease. So this is the kind of the grease. And again, as I say, there is a myth. People say I will be able to reduce coefficient of friction or friction torque using the liquid lubricant. Not necessary. Here you can see the static coefficient of friction is an starting the friction torque is on higher side, and in earlier one of the table I showed, the coefficient of friction can go 0.25 also. So that's very high. While in case of the lithium based grease, coefficient of friction is more or less same, it is not changing significantly. That means if I go with a liquid lubricant, at least a motor which is required to operate the shaft in a bearing, power has to be very high. Otherwise, the motor will not be able to rotate the shaft. So that's why this can will cancel, and I'll prefer to go with this kind of grease. So by assuming directly or directly in the liquid lubricant will be always preferable, because it is less viscous and all, is not necessary. We need to really justify it in an appropriate manner. How do we characterize NLGI? How they done it? They use a method. What is it there? They use a cone and cup method. There is a cone, and there is a dial on top, and this is a complete grease. So the grease is filled in a cup, and this is a cone, and they release, right? So that's why we say the grease surface, they maintain the temperature 25 degree, they are smooth, and so you can see that this surface is completely smooth surface, right? And so that maintained in a proper way, that is specification. Then this cone is released, and they is allowed to dip inside for the 5 seconds. In 5 seconds, if this cone penetrates the grease by 1/10 of this value, that means in this case it will be 45 44 5, 5 mm, and this maybe 247.5 mm. If the cone gets into this within a 5 second, ranging from 44.5 mm to 47.5 mm, then the NLGI grade will be 000. That means it's extra thin grease, like a liquid only, right? Now if NLGI2, in this situation, after depth of penetration, and after 5 second, depth of penetration will vary from 26.5 mm to 29.5 mm. So that is possible. And extra, maybe say very strong or very solid grease kind of thing, which now in these days particularly nobody makes. Earlier people used to make for the railway boats or rail trains, but now they are not making because it is already not a much use. This is a 8.5 mm to 11.5 mm. So earlier this grease was used for the sliding bearings which are used in railway. Now those people have changed to the rolling bearing, because rolling bearing is a much better advantage compared to the sliding bearing. So this is the NLGI grade which I have defined in this manner, and then this is what diagram it shows. The depth of penetration, what is the initial position, you are able to see initial position, you are able to see after 5 second position, and whatever we say 8.5 to 11.5 mm, that's a depth from this to this. So what depth has been given. So this is very clearly established, and we don't have to do anything in this case. It's basically for understanding what is a soft grease, what is a hard grease. So in this case I will use this as a very hard grease. NLGI6 is a hard grease, this is a very soft grease. But these are the subjective word, very soft, hard. So that's why this quantification method is a far better. Whether NLGI grade is a 000, 000, 0, 1, 2. As I said, that this NLGI2 is more extensively used compared to other greases. And then if you want to go lesser than that, then we can require a pumping. If you go for more than, even once in a while we grease the parts, that will be more than sufficient. Now what are the even I may start mentioning that it is a better in compared to liquid lubricant, but I want to just write down all those things. So major thing is that it remains at the application point, it adheres to the surface which is really required for our purpose, and reduces the friction, right? So we showed one figure also. Even in beginning itself it reduces the friction. Liquid lubricant, many times they are not able to reduce the friction at the beginning, so we unnecessarily require a big motor to operate the shaft, while in this case it is not that much. Next one, as I mentioned, the less frequent reapplication, maybe once in a 7 days, once in a 14 days kind of will be sufficient. And even like I worked for the one cam follower mechanism, they used to do once in a day, so that's more than sufficient. Otherwise liquid lubricant, every microsecond we need to keep sanding the lubricant. Of course the liquid has a different advantage, particularly carrying away heat, carrying away particles, those are advantages. But if the situation arise, if there's a heat generation, then if there's no heat generation, why will I go with a liquid lubrication? If I don't have to remove too much particle which are getting generated at the surface, why will I use a liquid lubricant? So this is where we need to think about. It's very good for the inclined or vertical shaft. Liquid lubricant can't be used because of gravity. Whole lubricant will come down immediately and cannot be retained there. Another thing is that it has a sealing capability, so we don't have to really put extra seal. Particularly for liquid lubricant, we need to put an extra seal so that it should not move out of the surface, and it should not go to the environment. It has a good properties related to water resistance, reduce the oil evaporation. Now one more point is comes, it can really increase the life of worn parts. That has been shown. Now this is a suppose a worn part, I'm using word, and this is a pit. Now if I operate this with a grease lubricant, grease will fill these pits. and it will give a cushioning effect. That's what we say, it will give a cushioning effect. In this case, vibration will also be reduced compared to liquid lubricant, and the noise will also be reduced, so that whatever the deterioration which was happening, even though there is a the part has been worn out, but this grease is providing extra support to take some stress, reduce the vibration, and reduce the noise level. So this is a very important advantage of the grease in this situation. However, one more thing is that we were talking about EHL. We want to establish elastohydrodynamic lubrication with grease, and more or less, whenever we are using grease, the elastohydrodynamic lubrication mechanism is established. To some extent, it can go on lower side, partial elastohydrodynamic lubrication mechanism, but in this situation, we need to establish some equation related to film thickness. Now, when we talk about the film thickness calculation, which we'll be detailing in the next few lectures, we need to think about what is the geometry. Now, in the case of the elastohydrodynamic lubrication, which will be covering complete lecture lecture 11 on this, we find there is some sort of a lack of conformity. What is the meaning of lack of conformity? This is a journal bearing or a sliding bearing, we say journal bearing, and you are able to see there is a one convex shape and one is a concave shape. So convex and concave shape, that is a conformity. While in this case cam follower, this is a convex shape, this is a convex shape. So both are the convex shape. So there the elastic deformation is bound to happen. While in conformity point of view, elastic deformation happens only in extreme cases. We do, otherwise the film liquefaction will be developed, and there is a V-junction which will be discussed in next lecture. So that's why we say that in particularly conformable cases, which is happening into the journal bearing, tilting bearing kind of thing, we require only Reynolds equation to solve. Of course, if there is a temperature rise, then we require thermal equation also, and these two things will be the lecture 9 and 10th will be on the Reynolds equation and hydrodynamic lubrication. When coming to this non-contact and the non-conforming context, we require in addition elastic deformation equation along with the Reynolds equation. So we required more sophisticated solution. We already required a one Reynolds equation solution, which is regularly required from hydrodynamic lubrication mechanism. In addition, we required elastic deformation equation also, which is important in this case. And then we say because of the convex contact and elastic deformation, there will be significant increase in the pressure inside the contact area. You can see the contact area itself is a few micron, maybe say maximum 100 micron. In that 100 micron zone, pressure will be significantly high, and that will cause elastic deformation. Now we are not restricting to that level. We said because of this excessive pressure, there will be piezo viscous effect also, and the lubricant viscosity will increase significantly. That means if I use the viscosity as a x, quite possible viscosity may increase by 20x. That means load carrying capacity of liquid will increase significantly, and that's why we say EHL is very important from that point of view. The tribose surfaces are bearing the load, but lubricant which we are using along with the lubrication purpose is going to really bear the load also. So that's why EHL is very important, and that's why we say the many time EHL lubrication is also defined as a piezo viscous elastic lubrication mechanism. So what is the major challenge? We required a simultaneous solution of three equations: fluid flow, Reynolds equation, elastic equation, and one is in this situation alteration in the fluid viscosity equation. So what is it really, what kind of equations are there? To understand that, let me just define first viscosity. We say viscosity is basically physical resistance to flow, which I believe that everybody knows. We measure the viscosity as a kinematic viscosity, and when we are using for the theoretical calculation of the equations, we prefer to use as a dynamic equation or dynamic viscosity. Right? There is a relation between the dynamic viscosity and kinematic viscosity, and there is a density relation. There are some common dynamic viscosity measured As I say, mostly measurement happens in centi-stroke, and whatever we are using equipment, of course, when we are using rheometer, we can directly find even dynamic viscosity. That's not a problem. But common equipment which we are using in in the labs, they are, measure the mostly kinematic viscosity, and mostly when you go for the table where you're going to pick up the some sort of viscosity for the some lubricant, mostly it is defined in centi-stroke. So you can see here that this is a thin oil, or maybe say the very less viscous oil, while this is a very viscous oil. So this comparison has been shown, the viscosity is changing. This is a less viscous and this is a high viscous oil. Now, why I am mentioning, quite possible that when initially under normal pressure, the viscosity is like this, and under extreme pressure viscosity becomes this. So I can say under extreme pressure viscosity, and how it happens, that is we are going to cover in next two slides, right. So normal and high and happens in situ in the that location itself, right. So for that purpose we do have a relations or some mathematical relation, and this relation is one. You can see here this is eta 0 meter the atmospheric pressure viscosity. There is some sort of component viscosity which is the pressure viscosity index component has been given over here, and as we mentioned that viscosity will increase drastically based on that. However, there is another relation also what we are giving, eta is eta 0, again atmospheric pressure, and with this in terms of pressure, but this is exponential relation. So here the exponent is one coefficient is being given, which is mentioned as a pressure viscosity coefficient, and it says this a value of alpha for most of the lubricant varies from 1 into 10 raised to minus 8 to 2 into 10 raised to minus 8 per unit Pascal. So this is done, and Z has been defined when in this available in literature, and then we are saying in this case particularly viscosity in Pascal second, this is the pressure need to be defined, and then this relation, particularly Barroux relation, is this one, eta is equal to eta 0 e power alpha p, while Rouland's relation is this one. You can see this is more complicated relation compared to this. Now when you solve the equation, Reynolds equation and elastic equation and pressure, naturally this will take a more iterations compared to this relation. The question comes, which one shall I use for our purpose? Naturally, if I assume simplicity as a main criteria, I'll go with the Barroux relation, simplicity as a main criteria. But if I see the accuracy, then I need to really investigate which relation should be utilized. So that's why I have developed small MATLAB code, because in this course we will be emphasizing on the MATLAB coding. We will not be developing all the relation, and most of the machine learning algorithms are available in MATLAB. So I'll be requesting to the companies to provide a complete the free license of the MATLAB to you for this semester course, and then you can do modeling on the MATLAB. So let's say MATLAB code. Here eta 0 is the viscosity, dynamic viscosity at the atmospheric pressure. For value initially I selected Z as a 0.6, then we are choosing initially the pressure as a 100 megapascal. I can vary. Now this eta is basically Rouland's equation, which we have described in previous slide, and then Barrou's relation is this one, right. So eta, and then here we are giving alpha. Initially we are choosing alpha as a 2 into 10 raised to minus 8, right, and here as I say Z we are choosing as a 0.6. So in this relation of the 100 megapascal, what is comes out, that whatever the eta which is predicted by the Rouland and whatever the Barroux, they are giving more or less same viscosity value. You find out this, you see that initial viscosity is a 0.05 Pascal second, while after under pressure of 100 megapascal it has increased almost 7 times, right. So this is a very important. Now when viscosity is increasing 7 times, the load carrying capacity is increasing significantly. So this is very important for us to understand that this mechanism is very essential for us. Now I change little bit. So you see now this, instead of 100 megapascal, I'm just checking at the 10 megapascal what is the value, right? Naturally 10 megapascal value will not vary significantly, right? So here this is the initial viscosity and this is a Barroux relation. So we have seen a little bit variation only, maybe around 20% variation in the viscosity, which is acceptable. But what Rowlands is predicting is something very high, almost 6 times, which is not possible. So I say that 1 to 100 megapascal I can go ahead with a Barroux relation, right? But if it is more, then what? Here your pressure is a 1 gigapascal. What happens at the 1 gigapascal, you can see Barroux relation is giving very high viscosity, unimaginable. That means Barroux relation should not be used. However, eta in this case is acceptable to us. So this is what we say the Barroux. If you want, if it is a on the P max is P max or maybe the location is lesser than 100 megapascal, I'll choose Barroux relation. Beyond that, I'll choose a Rowland's equation. And this is the beauty of machine learning algorithm. I can provide if and but a number of statements, and I can really go ahead with various relations. I can cover more range compared to what this initial author have given a range. So that's the beauty of our algorithm, which we are going to explore, and that will be more useful to us. Now coming to the slightly variation, so instead of 0.6, I choose 0.4. Instead of choosing 0.2 into 10 to minus 8, I choose alpha as a 1.1 into 10 to minus 8. But still I find that Barroux relation is not working well with the 1 gigapascal pressure. So up to 100 is okay. Beyond 100, we will not go with the Barroux, we will go with the Rowland's relation. And now last slide of this lecture, you say there are some sort of recommendation. Again, these are just guidelines, not necessary we need to stick to that. It is a kind of a first recommendation. I'm using the word first recommendation. After that you can go for the iteration. This says very clearly what is the particular, it has been given per second, it's not a meter per second. So it is in this case particularly 1 meter second, we can say up to 1 meter per second the grease can be utilized. Beyond that, again we will go for the lubricated cases, and then this has been shown again, limit for the grease, limit for the rolling element. So initially we are choosing a grease, and beyond that we come to liquid lubricant. That means up to even 10 meter per second, they are saying we can go ahead. Of course, in my view, more than 2.5 meter per second we should not choose a grease, we should go for the liquid lubricant. However, there will be separation of the thickness, or what we call that will be more important to understand. Now they are saying here again the limits shown are broad envelopes. Keep in mind it's a broad envelopes, and it will change with the temperature. They have not accounted temperature, and then if the lifetime is different, the nature of the bearing is different, then again this will change. So this is the kind of initial recommendation, which kind of lubricant should we choose. As I say, for me, if the meter this velocity, relative velocity is lesser than 2.5 meter, I preferably go for the grease lubrication. More than that, I know the heat generation will be possible, and we may require a liquid lubrication for that purpose. So with this, I say thank you for attending this lecture. We'll cover more topics of a liquid lubricant and related topics in the lecture 8 to 11. Thank you.